So hello everyone. I hope you're all well and in these virtual times and virtual conferences. I have a presentation. I'd love to speak with you about AI for Earth, the program at Microsoft and where it comes from. More importantly, I'd love to share with you the latest commitment, which is to build a planetary computer, and I'd love to get your feedback on that. But perhaps, and this is something I love to get your input in this, is if it's useful, we can also spend more time talking about something more in general. As Tao was saying, my background has touched GIS in different spaces. Like I was in the very early times in Mapbox, which is a company I think many of you know. Then I work also at the World Bank and other places. And if there are questions that are useful for you, that I'm happy to also talk about those. The slides I'm gonna share with them, so you can take a look to them more in your own time. There is some links and there is some resources. But I love to know, like, there is a chat window, and I love to use that one a lot. So just post their questions or comments. Like, for example, it would be amazing if you can post, where are you now? Like, which city are you attending this session from? I think it's going to help us have this session very interactive, because at the end of the day, this session is going to be useful if we learn something from it. And if you have questions, then I can guide the presentation also. So please put in the chat window, where are you coming from? I'm coming from Edinburgh, London. That's awesome. I'm in Alicante right now. Sheffield, thank you, Jorge. And okay, so wow, also Lebanon. That's fantastic. What else? So I'm gonna present the AI for Earth and the planetary computer, and then we can go for the questions if you think it's a good idea. So, there's some noise in this thing. This is the first time I use this. But it's good. That's fantastic. Jakarta, Indonesia. Wow, it's gonna be very late in Indonesia. Okay, let's go with the presentation.
Sorry, can you please mute the noise when people type in things? Okay, thank you.
I don't know. Yeah, okay. I wanted to do that, but I don't know how to mute that sound. Is it possible? Looking at Guansen or Tao if they tell me something, because
I think that's Guansen in charge. Okay.
Yes.
You just go ahead with your talk. Yeah.
Yeah. So in notification settings, there is a collaborate pop-up notification, and probably this is gonna stop it. But I love to keep having those messages. So please keep typing those. I'm just unticking all of those things. We are all learning about how to do the virtual conferences and virtual work, and I'm convinced that virtual conferences is not the same as physical conference on a screen. I'm convinced we need to use some other tools to make it more interactive and useful. And hopefully the window is useful to do that. Okay, so let's start with the presentation. As Tao was saying, I joined Microsoft 2 months ago, but the AI for Earth has been working for a couple of years. And it comes from the Chief Environmental Officer of Microsoft, Luca, and the very top from the President, Brad Smith, right? And Microsoft has made 3 big commitments. One is carbon negative at 2030, and historically, going back to the creation of Microsoft by 2050, it has also committed to protect more land than they use. And the third commitment has been this planetary computer. So this is a commitment that comes from the top, and this is a work that is being done from the highest levels at Microsoft. And I guess the main takeaway from this presentation is a couple of things. One is to point to the idea that I'm sure many of you already have, is that environmental sustainability is deeply intertwined with many things, not only with climate change or climate or agriculture or water or conservation, ecology, biodiversity, but also social development, socioeconomic development. And if we really want to address these and to help solve them, we need to understand those interactions. So this is something that traditionally is much harder to do. When we do research, we try to isolate an issue and then have a hypothesis and then work on that hypothesis. But when you start working at scale and you try to then solve those issues, it's a big leap between those hypotheses and research, and then to understand the systemic effects of it, how one interacts the other. The second one is one that you probably know very well, which is that geospatial is really hard. Doing geospatial analysis, the spatial joins, the buffers, all of those things, it's hard to do. It's hard to even get your head around how to operate with this kind of data and this kind of operations. And doing geospatial with the cloud, whatever cloud it is, so in your premises or one of the commercial clouds, it's hard to do. Doing it at scale, it's really hard. The complexity grows a lot. The computation needs for making, you can make an NDVI, for those who know what it is, very easily in your computer for a region. But if you want to do the NDVI for the whole world or for a continent for many years and see how it evolves, it's really hard. And that's something we need to recognize, and that's something we need to get easier. It's not sensible to ask for a PhD in ecology to do your work, but also a PhD in computation science to do these kind of computations, right? And hopefully, there are more and more tools to do this, and this is some of the stuff we're gonna be working on. The third one is that machine learning, AI in general, is also hard. Deep learning, for example, is one that has been used a lot, and it's really not easy to use. Again, it seems like you need 3 PhDs to do your work, one in deep learning, one in cloud computing at the scale, and one in your topic. So that's something that we are working to make it easier, and that's where we hope to get your feedback as we're trying to make it easier to do your work. And this is exactly what AI for Earth is. It's 3 pillars that go into helping these issues. One is grants. We give grants for researchers, NGOs, but also companies or anyone who's working on AI in general to Earth, thinking about all the issues that I shared about in conservation, biodiversity, climate change, water, culture, all of these issues of sustainability that we just call AI Earth to make it easy. It's what we have grants for. You have the link there, and you can request up to $15,000 on credits to run on Azure on the cloud, and it's always open. So just feel free to go now or after the talk maybe to request to have there's a small form of what you're going to be using these for, or what's the process and how much money you need to do to have those credits. So that's the first takeaway, useful hopefully for you, is that you can ask for grants to run your research on Azure. The second one is data. As I was saying before, doing things on the cloud is different, and it's different in many ways. One of them is that a lot of times we need a vast amount of data from sources like Sentinel or Landsat, or more that are local, and having those on the cloud makes things much easier. Not only because then you can download the data that you need easily, like give me all the rasters for London, for example, for the last 15 years, but also because if the data is on the cloud and your computation is on the cloud, then it's much easier to do. So that's exactly what we are doing with this pillar of data. So again, the takeaway from this, take a look to the data we have on Azure Open Data, and if you see something, just use it. And if you don't see something and you think it's useful, let me know, and we'll work with you or whoever's the provider to put it out there. We know that we are not the only ones doing this, and we know that we are late to the party. AWS and Google have done an amazing job putting these data sets in the cloud, and we want to also make sure that when you do your work, you have the data you need for that. So also, please feel free to share the data that you need. And the third one is building tools. Like one of them, and I'm going to go in detail to these pillars. One of them, for those of you who work in this, is camera swaps, which is basically you place a camera on the forest, and then you take 1,000,000 images, and then you need to flip through all the images to figure out which ones have animals or people, and then classify those animals. So we build tools so that the researchers spend less time. Literally, for some people, going through a stack of millions of images is their work to filter them to the ones that have animals, which might be like 3%, 5%. So the researchers upload the data to this tool, and then it comes back to the ones that have the animals. So we have done more than 600 grantees. This slide, of course, is always outdated because every time we update it, there's more work we've done from more than 80 countries. So this is a global effort, and we love to help everyone working with on sustainability. This is the gallery. If you go to this website, you can see the gallery of many of our grantees, which also helps to promote their work. Not only has the work they've done, but also the code. If they release the code openly, we can also put a link here or related resources. I was looking at the proceedings of this conference a couple of days ago, and I was skimming through all of the proceedings, and I can see many of the papers that are being presented in this conference could very well be here or be helped or by this grant process, or the other way around. We love to get, when you do your work and you use some tools to see which tools are using and what would be useful for you. Is it that you need more computation, you need more data, or whatever it is. The second one I mentioned is as I said, is the data set. We have Landsat, Sentinel, the digital elevation models. We have NAPE, which is only for the US, but hopefully, I think they have the same in the UK and other countries. And we love to get pointers to those and then upload them, because once you have these high resolution aerial images, then it's much easier to do the work. From the high resolution, like drone data or NAPE data, to MODIS, which is much lower resolution. To do that, also the data for each of the data sets, we have code, so you can get documentation. And this is something I love to hear from you. Like if you put in the chat, like when you do your work, I love to know if you use, for example, Python, or you use R, or you use. Oh, thank you, Tao, for putting the grants there. Again, I'm gonna put all the presentations so you can see all the links. But it would be amazing if you can tell me what platforms you use to do your work. Do you use Dask for distributed computing? You use Python? You use R? You use MATLAB? You use I don't know. You use Pangeo, for example. For those who know what this is, Google Earth Engine is a really good IDE. It's a really good tool to do at scale. In our view, Python has a lot of potential and is widely used. But it's also true, and I'm seeing here, like example, Michael or Adrian are using R much. So the market share, I don't know how it would be, but definitely R and Python are on the top. Thank you, Phil and Christy. So let's go to what I was mentioning before. If you have data sets that you like to have and you don't see them in the cloud and you like to see them, please let us know. If you have ideas for formats that you really like and are annoying to you, then just let us know which formats you like more. For example, in raster data, which I'm sure many of you use, in the kind of revolution that has happened with the cloud optimized geodiff, and we try to put a lot of data in this format, the COG files, because of several reasons. It allows streamings, it allows to ask the particular question in detail that you're asking for. Save files. So who likes save files? Thank you, James. So this is the question. For example, I was gonna talk about save files now. In raster, we have COGs, these cloud optimized geodiffs, and I think they solve a lot of issues. What is the equivalent of vector files? Save files are the standard, and there are many things you can create as a save file, but they are the standards. They are able to gather small data sets and huge data sets. GeoJSON, for example, which is a format that I love, it's great, but doesn't really scale much. Like imagine and this is something I was thinking about last week. We have a data set, a vector data sets that is like 10 gigabytes. What did you use this data on? Like you cannot put it in a GeoJSON because it would be fantastic. I'm sorry for those I'm going very technical in detail. It's gonna deep toes in a few issues, and those who know about these issues, please just ping Just tell me what you think about it, and those who this is not something you work on, that's fine. But this is the kind of questions we love to hear. For raster, we think COGS is a great tool. For vector, there's not something similar. So if you have, like, for example, Bruce seems to like save files because they're fast, and that is true. But James doesn't seem to work like save files. What would you suggest? Geo packages. This is a really good one. I don't know if they allow to directly query. Like, if you have a massive geo package on the cloud and you wanna request a particular section of it, I don't know if it allows to do this kind of streaming, which is basic for the cloud. And this is what it combines several tools. Geospatial and machine learning combining is that create these needs. In geospatial, there have been several formats with these benefits and drawbacks. But for example, for machine learning, one of the key parts of machine learning is training data. In essence, when you create a neural network, when you train a machine learning algorithm, you give it a lot of examples with a lot of labels in one of the types of machine learning to then have it train and create those labels when it sees new data. Now, it is very crucial to have very efficient ways to train these machine learning networks to be able to train with both the raster and the labels. And ideally, you have a way to generate a lot of data on the fly, asking for a small section of the raster with a small section of the labels. This is not possible today with many of the standards that we have the data from. Ideally, we find a format that allows to do this kind of training data on the fly streaming. Experiences. We love to know what experiences you've had with working with some tools, like what you like, for example, of R or PostGIS, or what you don't like. What are the things you like the most from example, Google Earth Engine, or what things you think could be improved? That's the kind of thing. Because at the end of the day, what we're trying to do with AI for Earth is helping you create better research faster, so that you don't spend 80% of your time gathering the data and put in the right format, and put it in memory or put it in a cluster, so that you can start doing your work quicker. So that's the keys of this presentation. And I'm going to put a lot of examples on this, hopefully to make the case. These are some of the examples, not only camera traps, we also work to create tools to detect from aerial images animals, or we also created tools to detect animals on sounds, like when you record the sounds, especially in oceans underwater, you have microphones and you listen to the sounds, and then the algorithm detects if it's this or that animal. Also land classification. There's a lot of land classification that could be trained again if you have the save files and you have the raster. Then you train a lot of data to see an image, and then say, hey, this is grass, this is city, this is urban, this is paved, this is not, and then to use those tools in other places where you don't have the data. There are some limitations, and as I'm going to talk about, but that's basically what we do. But here's another key point I wanna share with you. There was this paper, I think it was yesterday. It was yesterday that was published in Science, and this paper goes to measure what happens if you double CO2, and then what happens with the temperature if you double CO2. And the researchers came out with a conclusion, but to me the punchline is not the conclusion itself, is that it took a lot of time to make this research. It took 4 decades to know this answer, and hopefully we find a way to make it easier, so it's much faster to create these answers. We are not claiming that you're going to be able to do these studies lively or update them, but if we are able to make a structure so that we can replicate the study much faster, or we can have a structure where you can analyze the data in a faster and more efficient way, then that will be fantastic. Otherwise, we will see this cadence of biodiversity reports every decade or so, or these kind of very landmark studies to figure out this is really helpful for policymakers and to make the call for action. But if we need so much time to do this data analysis, then it's much harder to do. Again, another question I have for you: what percentage of your time do you dedicate to not doing your hypothesis testing or the scientific method? What what percentage of your time you spend on, let's call it non-thinking time, like downloading the data, getting it in the right format, setting it up, and have administration emails, just put them aside. I think it's another problem. I don't think we'll be able to help with the emails that you have to do your work, but when you do your work, well, I'd love to know if you spend 80% of the time with the formats and the data, or you spend 10% of the time. And if you are one of who spends only 10% of the time, I'd love to know how you work on that, because in my experience, it's not the case. As you answer to that, I'll go to the next step. What I share with you is this AI for Earth, which is this data, computation, and tools. We've seen over a couple of years, helping a lot of people, that there is a lot of work that is could be reused. Like someone has spent a lot of time, and then someone else does the same, and someone else does the same. And there is also a repetition or a need to this kind of data sets, or a need for this computation environment. And we also see the need to have a place where you can go and ask, where are the trees in the world? Where is this ecosystem happening? What is this ecosystem where it rains this amount? What is that there is this close, for example, to the river or to the sea, that has this boundary environment, these inputs and outputs? Or what happens if this environment, you do this and this changes, and there's less rain? If we change from grass to urban in this section upstream, what happens downstream? And we kind of know the tools to calculate this, but it takes a lot of time to create the environment to do the computation and to analyze data, as I was saying before. So this is what the Planetary Computer is. This is a commitment from Microsoft to create an environment where you can ask these planetary questions of what's happening where, or what would happen if this were to change. Ideally, this is something that then researchers can use, but not only researchers to create more knowledge, but also NGOs or companies when they do their work, they do, or governments when they do the inventories or the assessments, the biodiversity assessment, and then we can register that and see what happens over the years, or see what's the impact of one or the other policy change or change in those environments. That's what the Planetary Computer is, and this is a cool job alert. We are opening for a couple of positions, probably one more, and if you'd love to join our team, just click those links when you get them, or just search for AI for Earth jobs, and you'll get them, or just ask me. I'm pretty easy to reach, so just let me know if you have questions and you'd love to join the team. We're looking for someone with knowledge on architecture, and someone with knowledge on data sets to help us with that, so that you can all use it. Well, I can see in the chat there is a very very opinionated conversation around software and X11 and Google Colab. Google Colab is great. This is true. This is the kind of innovations that I love to see more. Like, for example, imagine if all the work you've done in all the proceedings in this conference, they had a button that says just deploy, and then you enter in the same space that the researcher had when they published when they created this paper. You can see the graphs, you can replicate the graphs, you can compute again, and you can change the hypothesis, change the data to your work. That's also one of the goals we'd love to see with a Planetary Computer, which is a little bit what Google Colab is doing today, which is, I think, it not only goes to help researchers avoid replication, it goes to the replicability of science. It goes to be able to replicate what someone else has done, and also improve it or change it to your own needs. I'm gonna go in few areas. One is on climate change, the first one. The other one is in conservation, and the other one is in land conservation. So sorry, land conservation, another in biodiversity conservation and climate change. The rest of the talk is examples of work we've done with different clients, which I think is fantastic to brainstorm and see what can be done. And this is where I wanted to ask you if you want to have more time for questions in general on on experience I had with Mapbox or with the World Bank working on GIS, or with Satellogic, the satellite company, of other things, more in general, to have an open Q&A. So if you rather hear examples, just say, hey, I would love to hear examples. And if you want to have a Q&A that is longer and more general, then also please let me know on the chat. The slides are going to be available anyways. So let's take a moment to see what people want, because at the end of the day, it's for you. This session is useful if it's for you, useful for you. And if you have to do something else, that's fine. My preference for case studies. That's great, Sarah. So on machine learning, there's a couple of avenues that we focus on machine learning and climate. One is on carbon markets. Subseasonal forecasting is another one, and making climate scientists more efficient. On the carbon markets, this is a work we've done with Silvia Terra. This is a company that some of you might know, which is basically to analyze satellite data and other sources to make an inventory of how many trees are there in the US in this case. So this is something that they were able to do at smaller scales, but doing it at higher scale needs the process to be extremely efficient so that it can scale. Even with the resources of a very infinitely scalable cloud, you have to make sure that it's efficient, but also the scale of the data you need and the computation also needs to be scalable. So that's what the work we did with Silvia Terra is, that we analyzed, or we helped them analyze the whole continental US to map how many trees are there in the US, which seems such a simple question in terms of sustainability. So you can ask these questions over time and see how it's changing. Or how many trees are there in the world? What is the stock of carbon of those trees? And if you burn them, what would happen if you plant more? James says, would like to see cool stuff you're doing at Microsoft. Okay, so I'll present some of that, but hopefully you see it's cool. So subseasonal forecasting is another angle that we've helped in. Subseasonal, it goes in between weather forecast, which is the short term, and seasonal forecast. And seasonal forecast, the highest degree of certainty comes from weather forecast, and these models are pretty good at forecasting for 1 to maybe a week. 2 weeks is not really good because of the kind of physics that is involved at the small scale and the small region. Then the accuracy goes pretty low quickly. But for very short time frames, it's very high accuracy. Same thing, fair accuracy for seasonal forecast, and longer ones. That's more the climate kind of things versus the weather. But subseasonal forecast is something that is really hard to do. And some of the work we did with Columbia was to analyze this and to release data sets. And this is the URL that you can see more. It's more like competition, and to figure out models to train these models with machine learning to increase the accuracy of subseasonal forecasting. That leads me to one of the tools that I think I haven't seen mentioned when I was asking for the software that people use before, which is Pangeo, and I talked about it. I love Pangeo. Pangeo is an open source ecosystem of tools that includes things like Jupyter, like Python, and other tools that is basically a closed or a packaged ecosystem that you can deploy and then do your work much easily. It basically, think about it like if you want to click on it and then you deploy some environment that you can see on the right, where you can start working with data already on the cloud. So that's, or anywhere, you can also put it locally. We partner to make this the OI cloud resource, which allows people, especially working on oceans, to do their work. And this is the kind of thing that also works with subseasonal forecasting, but this is the kind of tools that we love to see more, because if you have this Pangeo instance, then you can spend less time deploying your own resources. Let's go to biodiversity conservation. I think many of you already know that this is in decline. 25% of species are threatened with extinction. And this is a big problem. This is something we need to measure so that we can talk about it accurately and then take action, especially in those places that, thank you, Tayo, take action in those places that are seeing the rapid decline in biodiversity. So there is also intertwined biodiversity with climate change, because climate change is a driver of diversity loss. It's particularly a threat to ocean diversity. Climate change is a threat through acidification and sea level rise for coastal and ocean biodiversity. Also in the Arctic, which is where you can see the effects of climate change more. And it's also a driver of desertification and productivity changes. So there is, as I was saying in the beginning, when you talk about actually any of these topics, when you talk about biodiversity, sustainability, ecology, climate change, all of these things have heavy implications, upstreams and downstreams and horizontal. It's amazing that I would say we don't pay that much attention to these interlinks between these technical areas. I'm gonna go a little bit quicker for working to talk about this. Some examples we've worked with Wildbook and WildMe to identify, not only identify which animals it is, but also identify if it's the same one, which is crucial for migration patterns. So is this the same dolphin that we've seen, I don't know, 3 months ago somewhere else? Is it the same whale shark? So this allows to identify the migration patterns and how it changes. And one way to do that is with machine learning. So again, you have to then pay attention to the particular patterns on the skin of the animal or the fins. We've done some work, and actually this is another resource that could be interesting to take a look. For those of you who already work machine learning on biodiversity, especially with animals in general, more than plants and visual images of animals, not sound or other ways, we've created lila.science that you can go there, and to my knowledge is the biggest collection of images that are labeled to do training. It has literally, I don't know, more than 20 million images of different data sets from different regions of the world. There are several in Africa, but also South America. And if you want to work on, and some of them have individual tags, so you can also work to train of these new techniques for identifying not only the class that is there is a tiger or it's something else, but also the individual, if it's the same individual or not. So lila.science is something you should take a look. With iNaturalist, we've also helped iNaturalist, which is basically, many of you probably know about it. You take an image and you can identify what plant or animal it is, and we've helped them to improve their machine learning model and then create a beautiful map of what people are recognizing where, which is another way to map to make an ecosystem inventory of what's happening. You can also take a look to iNatural, and then there's some comments, there's some questions. You can tag these pictures, and then you can contribute to those efforts. There is more work we've done with in this competition. So for CVPR 2019, if you know about this conference, it's computer vision. And every year there's a lot of progress, and there's an opportunity to share with people not only the progress but also the code, and this is something you can also take a look. This is another example we've done to use machine learning to find penguins from images. In general, all of these efforts, for those who are not that familiar with machine learning, they require basically the same thing. They require a collection of images and a collection of labels. And then you tell the machine, this is the image, and this is the label, this is the image, and this is the label. And then you do that for millions of cases, and you hope that by training the network in this way, then you give it an image, and it tells you where the labels. So that's basically the same thing. You can do that with images from space to see penguins. You can do that for camera traps to see the tigers in the forest. You can do that also with sound, with the spectrograms. Another one for detecting seals in satellite images, which is again the same. You take images and then you label them, and then you train the machine learning algorithm to do that, to infer the labels when it doesn't have it. These are some of the links if you want to know more about it. There is the camera trap surveys. There is the for aerial, acoustic, and also land cover surveys, which I'm going to talk a little bit more later. And all of this is available. All of the data is open source, and all of the code is also on GitHub if you want to take a look to that. On camera traps, we've seen is extremely useful. I've already mentioned them, so I'll go quickly on that. But the idea is what I said before. You have a lot of images, and you want to filter those who doesn't have animals or people or something else that you're not interested. Typically, the hype has been on detecting directly exactly what type of animal or even what individual, which is what the word also I shared before. But often, just having a rough detector of there's an animal here, or there's some person here, or a vehicle here, is also really useful because it allows to make a first pass and then also only retain the small percentage of images that have the thing you are interested about. So then you don't need to work with a ton of images that don't have any labels, but also with the smaller amount of images, which then you can tag for the individual level or the species level. And this is what we developed. This is our camera trap. It's called Mega Detector. It's globally useful to detect, and then we've done some classifiers once we detect that. The whole code is also in Google. It's trained on the datasets from Lila.science and other datasets, and it's trained in TensorFlow for those who know about it, and it's trained only to detect any animal, any kind of animal, any kind of person, and vehicles. So you can use that to then pass it, make a first pass of your images and work on that. These are again the codes. When you have the copy of this presentation, you can use them to take a look to that. And again, this is the Lila.science to work on that. There's other uses that of detecting that is not only biodiversity, it's enforcement. You can use the same technique, exactly the same, to detect fishing boats in regions of the oceans where there should be not fishing boats because they are protected areas. If you have images, satellite images, then you can see if you detect a ship inside those images. It's basically equivalent of making a spatial join if you have the tracking from the beacons and the regions of these protected spaces. You can also use it to, as I was saying before, to detect an individual that is in you have a camera trap and this a region that is shouldn't be. Or cars. That's also why we have cars, is to detect if there are cases where there's a car coming with several people, and if you detect this, then you can send a message with an SMS. Like, for example, if you put this code into a chip phone, which is easy to do, and then you put it with a little solar panel, then you can put it in a region that it should be protected, and then if it finds a vehicle or a person, it sends the SMS. It allows you to have a very high degree of cognitive awareness. There is a vehicle or there is a person, but only send back the information when that happens, which is much cheaper than sending the whole stream of the camera, like a webcam or something like that. Same thing for combat poaching and seeing where the elephants or the people are. This is also useful. This has been done also with drones, flying drones during the day and also during the night with thermal cameras, which again needs exactly the same process. Training data, labels, train, and then you have the machine learning that does that. This is less on sustainability, but it is actually it's on poaching. So there's a connection, which is a work that we're doing with the Heathrow Airport, which is to pass the suitcase that goes through the airport and the X-ray machines, and then just detecting those that have skulls or animals that they are trying to smuggle into the country. And again, the same idea that you don't need to put the whole machine learning train network or training it. You just need to put an edge device, which is a device that has only the inference way, which is just, I was saying before, you have the images and the labels, you train for it, and once you train for it, which is the expensive thing to do with GPUs and all this complicated computing, then you can use much much more normal computer, which is an inference model, and then you can run it quickly. Land conservation. Again, I'm going to go quickly here because it's only 15 minutes. One of the key points of land conservation is to also know what's the land use and how the land use changes. And this also has strong implications not only for land use and agriculture, but also for water and how water sets are able to capture the water and then avoid, for example, the flooding downstream. So if this grass is easier to do, and if there is a lot of change in this land use, can have huge implications in the whole ecosystem. It also has implications when you want to make a dam, for example, to make a reservoir of water. What's going to happen around the dam and also downstream of the dam. And some of the work we've done, I'm going to go a little bit quickly, is to optimize the land we protect, to minimize the land we use for food, and to making land surveys more efficient. So this is what we've done with NatureServe to map the importance. There is a metric that you can construct called biodiversity importance, and then doing again it at scale needs a lot of heavy computation, and that's the work we've done with NatureServe. With Nature Conservancy, we've done a similar work where they came up with a metric called last chance ecosystem, and again the beauty of the work here is that the researcher or institution has able to figure out with experts in the field to create a metric called last chance ecosystem. But once we have that metric and you prove it in different places, doing it at scale is really hard. And that's when you have to start working on those geostacks or Dask or all of these tools that need to scale away that scale to do the entire work. And that's where it's very tricky to do, and that's where we are finding the most use for the planetary computer. That again is the reason we love to get your feedback for this. This I already mentioned in the beginning that the Microsoft has committed to protect more land than it uses. This is how the amount of land we use, and this is how it breaks to, like, it's mostly computer centers, and we commit to protect more land that we use, and hopefully other institutions or other governments they also follow with these commitments. There is again, I'm going to go fast here, but the idea is to have an image of the plot and then figure out with labels where the crops are better, will give more yield or less yield, and then you train the network algorithm and you figure out which places are best to plant your seeds or which places you should focus on doing more irrigation. That's the work we've done with Ag Analytics, which is a tool to help farmers not increase their plots of land, but be more efficient in the plots of lands they use, or identifying with the different sets of criteria which plots of land are more suitable for the crops that you're planting. This is an example of what I just mentioned. If you have this image aerial, then you can see some roads, you can see some ponds, you can see some buildings, but doing that automatically to show that then you have more quantitative information, it's very time consuming, and hopefully now with these land classificators we can do that. And actually we've done that for the entire US. And in fact, one of the latest works we've done is to use the high resolution data we have in some regions, like the Chesapeake watershed. We have it at a very small scale, this land classification. It has taken 10 months to do that. It was $1 million to do this by the Chesapeake Conservancy. Now, if we were to do that in the whole US, it would be extremely expensive and it would take much more time. This is just some back of the envelope estimations doing the same thing. Obviously, this doesn't scale. And this is where these kind of tools are extremely interesting, because if you're able to figure out a way to train the data we have everywhere in the US and the data we have only in the Chesapeake watershed, to create a very high resolution images, very high resolution land classification in that area, if we're able to do that without needing the high resolution images from that region, then we would be able to expand this work and not only infer what is on the Chesapeake watershed as the training set, but then do it for the rest of the US. And that's exactly what we're doing as part of the Eye for Earth, is that we've used NAPE, which is the 1 meter resolution for the continental US, and Landsat, which is 30 meters resolution, and then combining those two as the input. Then we train with the labels, in a sense, of the 1 meter resolution land cover that we had for Chesapeake and another land cover we had for 30 meters. So we figured out to make, for those of you who know about this, like super resolution, hyper resolution from a set of inputs to figure out the land classification. And this is a demo of that. You can take a look to the demo. And you can also play with it and correct it, and then help us do these land cover predictions, or use it for your own region. We are only 10 minutes out, so that's why I'm gonna cut here. Again, I'm gonna share the slides if you wanna see the examples, and I love to open for questions on this or questions in general that I can help you with. So fire away questions. Let's go to the chat and see. Well, if you have questions, please put it. If you don't, just share the part of the work that I presented that could be most useful to use, like if you're working on biodiversity, if you're working on surveys, on camera traps, the tools that you use that no one has mentioned, what you struggle with the most as you do your work. That's the kind of thing we love to know. Hello, Dao.
Yeah, Bruno, thank you so much for giving us a very broad overview about Microsoft's AI for S, actually AI for Good. Of course, it's part of the AI for Good, which is really good to us have this overview about it. So maybe I'm waiting for other people's questions. Maybe I can ask you one or two. So first, I noticed in the grants you mentioned about. So the grants I saw, one is actually we can apply for the computational resource if you want to use your platform, so we can get some credit for that. And can you mind say a little bit more about it? Say what anything specific when if we really apply for it? It's any any tips for us, or even including bot grants. So other people, please just type in your questions on the chat. Thank you. Yeah.
I'm gonna share my window again. If you go to that website, like literally, if you Google AI for Earth grants, you'll end up in this page. Yeah. And if you go to the page, then you I just changed the window and how to apply. Here it is. Yeah. So I should complete related grants. It's not only credits. If you need other help or more scale of this, just send us an email. I think the email is also some here, but if not, you can email me directly. And then you can ask for $5,000, $10,000, or $15,000 in credits. And basically, all you need to do is always open this application, and just to make it easier, every July, October. But if you cannot, the next one then would be in October 5th to get those credits. If you cannot wait for those, then again, fill the form and then reach out to us, to me, for example, say, hey, I just sent this one, and this is the program. I love to get expedited credits. And it's just that is just click on the online platform and you just fill it up, and that's it. It's very easy.
Yeah, thank you. I think James got one question for your request for you. So can you talk a little bit more about how you went from rocket scientist to where you are now? You have a very interesting career so far, I think so. We just have a slightly chat in the beginning because we don't have enough time. Maybe you can say a little bit more. How do you, move around from the career path?
So James, thank you for the question. To me, is the most important fact. Not what I did, but the most important thing is that most of you are researchers, most of you are scientists, and most of you deeply care about sustainability and deeply care about solving the issues of climate change. And I would say that it's not only the research that is going to get to the solution. Of course, we need research. Of course, we need answers. But it's not only data that is going to be those answers. There is a distance between the published paper and the action. And that path is not only the politicians or the governments paying attention to the scientists. It's many other things. It's behavioral insights, is architecture decision, is personal choices, is culture, is diplomacy, is many of these issues. And that's the reason, or when I was an astrophysicist working on solar physics, I felt I wanted to do something, but I also felt there was no connection between what I was doing or caring or my skills to having an impact in society. And that's exactly what I started trying to answer this question. There's only like 5 minutes left, but I published a whole book about this. It's called Impact Science, and it's on Kindle and Amazon, all that stuff. But I'm happy to give you, every one of you, I don't know if you can share it directly in this chat, but there's, I'm gonna try to share the whole document with you with the book. It's a very short book, and it talks exactly about this idea. I went to Greenland. I saw how the icebergs were melting, and I knew that it was because of the cars and the industry that was happening very far away, and it was killing my heart and my brain to know all of this, and at the same time not know how to help. And that's exactly the story, how I opened the book, and then I talk about, that's why I joined the World Bank. I didn't join the World Bank to talk about astrophysics. I joined the World Bank to figure out how we can use the skills of science, the skills of knowing what a special join is, the skills of knowing hypotheses, the skills of putting in a map together the poverty metrics, but also the nature metrics, and figure out how they interact with each other. So now it's uploading there, but I'm happy to give you the book. Is in PDF form. If you need it in other form for accessibility reasons or whatever reason, do that. Hopefully it answers helps answer the question. The gist of it is that it's my quest to try to have a real impact in society, to have a real impact in the challenges of the world. In my view, it's not only academia. Academia is extremely important, but we need to make sure that it translates into action. And I found that the Planetary computer could be a way, and that's the reason I joined. I joined Microsoft because of your question, because of figuring out how to of this strange path. Thank you, Emma.
Thank you, Bruno. Yeah, that's a fantastic answer. I think everyone can't agree more. Okay, you can say the comments. I think I got another one from Abigail. So it says, thank you for your talk. So maybe you can talk a little bit more. How can we create a better innovative environment for cooperating with geoscience or geospatial and machine learning technology? It sometimes seems that the community are quite separated. So what's your view on that? Yes. Especially you said in the beginning, it's very challenging. Yeah.
For collaborating. I think there are many aspects of this. Oh, it's only 2 minutes. I think a key aspect is to really talk to the people who live in the places that you are studying. If there's people, and there's not who interact with that place. Is it close to an industry? Then learn about that industry. Is it close to an indigenous people? Learn about those indigenous people. Really, I find that there is a really big difference about knowing a problem and knowing the ecosystem that surrounds the problem. Of course, plastic bags are bad, but everyone uses plastic bags. There are regions where the whole job of the people is to make plastic bags. You cannot cut the industry of making plastic bags because it's a problem for them. But of course, we have to do it because it's killing the environment. And that's how we can work together, is collaborate together with the external world, is to really try to learn the ecosystem. How we can work together between experts on geospatial and machine learning technology, reaching out. This kind of conference is hopefully the way to do that. It's a very proactive effort. I also see a question from Melda, which is what I see the AI for Earth in 5 years. I hope that in 1 year we have a version of the Planetary computer that sets the standard for lowering the barrier for any researcher, NGO, anyone who wants to ask questions about sustainability to do the thing. Hopefully it's replicated and used everywhere else. Hopefully it's not the only solution, because at the end of the day, the more everyone can work on this, the better.